Continues today with a talk by Gordy, who's going to tell us about string M theory, the Higgs boson, dark matter, and LHC.
Subtitle is explain. So I will try and talk about a program that's been underway since about 2006 with particularly Bobby Acharya, who I've worked closely with, and a number of students and postdocs. Yush Kumar particularly has played a major role in these. And since we're getting data now, we made a prediction in this program of the, we'll just check, mass of the Higgs boson before the reports of data. And then recently, there's been a 130 GeV energy gamma reported coming from the heavens. If that were true, it would be the first physics beyond the standard model that we found, and it would be the discovery of supersymmetry, and it would be the discovery of dark matter. And it was predicted in this program in its character and its type and the mass only vaguely approximately. There's a recent review that covers almost everything, not the very latest stuff about this guy, that we put out a couple months ago if you're interested in looking at a lot of that stuff. Whoops. Okay. So everybody here knows string theory is really hard, but we've been arguing that for some questions, if you sort of choose them judiciously, you can get around some of the problems and get some interesting answers under some conditions. And particularly, it was possible to do that about Higgs bosons and dark matter. So one of the messages I want to convey is that we're really into an exciting time now, not only with data, but with a theoretical framework that involves string theory and lets you make sense of things. So here's a longer list of what I'm going to talk about. I can easily finish the talk in 6 hours or so, and we'll see what happens. So I'm going to give a somewhat long introduction, trying to put off some of the many questions I get when I give talks like this. Sometimes it's faster if you prevent them. And it depends on the audience, of course. Then I'll focus on a particular result which is very crucial for many of the results, the relation between moduli masses and the gravitino mass. Of course, if you compactify, you get moduli in the string theory, and that's fine. And when you break supersymmetry, you have gravitino masses, and the fact that there's a relation expected between them in compactified theories where some of the stabilization is due to supersymmetry breaking has many implications. I'll mention the old cosmological lower limit on moduli, but then with this relation you can tie it to other things and make some of these predictions, and in particular that leads to a firm parameter-free prediction on the Higgs mass. It's parameter-free, but it depends on a couple of assumptions, and I'll try and make all that clear. At this stage, it depends on assumptions. They're checkable and removable. And then I'll turn eventually to the LHC predictions for a little while at the end, and make some final remarks. So we don't solve the cosmological constant problem. You know that. Our attitude is, and it's the standard attitude in phenomenological areas, that the cosmological constant issues are very likely to be orthogonal to the rest of particle physics. Essentially, all of the approaches to the cosmological constant problem are decoupled from other things. So what I like to say is that when you look at how the Higgs mass prediction goes, it's clear it's not going to matter how the cosmological constant problem is solved, and not solving it is not likely to prevent it, and solving it isn't likely to help it. There's actually a nice analogy that people who like to think about the impact question should should pay attention to with the strong CP problem in QCD, where you successfully ignore it, it would wipe out essentially all QCD predictions if you included strong CP effects, but you ignore it and have from the beginning, and it doesn't change anything. In practice, we sent that the potential at the minimum to be very small compared to anything else in the problem, and we checked numerically that that works fine. You can do it.
Okay. Can I disagree with that?
No.
The thing is, I mean, we don't know anything about the cosmological constant problem. I mean, there's so many things that if you have a solution to the cosmological constant problem, it may affect low energy physics, and we don't know. I mean, that may change the whole picture that we have.
Well,
that's a standard criticism about.
So it's true, we don't know. I'm telling you our approach. If it's wrong, then we'll get some wrong results.
Right.
It can be checked. This is our approach.
No, that's okay. No, but for the cosmological, in general, comment about the cosmological constant problem, I mean, is if we find a solution to it somewhere, somehow, that may have impact at very low energies that may be changing even our picture about low energies for symmetry or so, because it's
It could, I agree. But our approach is that it doesn't affect the kinds of things that we're talking about, and if that's wrong, it'll be wrong. We think it's a sensible approach, and that's what we're doing.
A more concrete objection would be when you said essentially all approaches would not violate what you said. The one I gave yesterday would have violated what you said, so it's not true that essentially all approaches. One way to say what Fernando's saying would be that the issue with the cosmological constant is a low energy issue, so you have to modify the low energy physics. And so you can assume what you want, but it's not true that all the approaches don't do this.
So most of the approaches I know of in practice do not change the prediction for the Higgs mass or the dark matter or CP violation and so forth. So if you have one that for the cosmological constant that affects these things, that's fine. I mean, let's check it. But we don't know of any actually, but that just may be ignorance on our part.
Well, so yesterday there was talk on one.
I missed the Higgs mass part. Okay, so another question that comes up all the time is how do we find our string vacuum if there's huge numbers of string vacua? And actually what I'm going to do today effectively is produce, in a certain sense, a candidate string vacuum, because many of the phenomena that our string vacuum, or at least the one I live in, which I assume you all live in too, I will show that many of the problems have consistent solutions or approximate solutions from in the point of view that we're taking. So it's a good start on that. And so it takes you a long way towards solving this problem just in practice by combining things like stabilization and looking for solutions of certain problems and looking for vacua that can work in our world, ones that we can live in. So by the end of the talk, I'll make more clear exactly what I'm saying here, but I'm going to address this in a practical sense as I go along. Of course, I agree completely that if you only use top-down physics and no restraints from cosmology and data and other things, that you were extremely unlikely to end up in our string vacuum, but that's not what we're doing, as you'll see. We use the word generic a lot, and it more or less means, or will mean here, things that aren't theorems perhaps, but they hold pretty generally, and it's what you do if you just go along naturally and don't adjust things or work hard to construct things. So some of the arguments I make today will probably be generic. I'll mainly focus on the arguments coming from the M-theory compactification on a manifold of G2 holonomy. But many of the arguments will be much broader in practice, and if they are, that's great, and then they apply in other areas too. I'm not focusing on that or pushing harder on that, but I don't mean to claim at all that they're, in many cases, special to M-theory. Clever people will certainly be able to construct interesting non-generic models and test them, and a lot of you are expert at that. So we'll see how that goes. Now, our work has focused, well, most work in the field has either gone toward looking at the compact manifold and embedding the MSSM or generalizations of it and the zero modes. What we've done instead, motivated by a goal to be ready for LHC physics and for dark matter physics and such things, is look on the opposite side, where we focused on looking at the moduli, stabilizing them, generating a TeV scale, and looking at the soft breaking Lagrangian and the predictions, and got pretty far with this. Particularly in the case of the G2 manifold, you know that there's no metric known yet, and so it's very difficult to work over here. There's been a limited amount of work, which I'll mention in a little while. But it's just not been our focus, partly because this has gone along well and been able to do a lot of things. And we would, of course, like to work on the metric. Another sort of general talk which comes up in certain parts of the US and at CERN, I guess, and maybe I gather here today, the subject of naturalness comes up. So, is your theory natural if you're explaining things, or is data natural? An amazing question. Suppose that there does emerge an underlying string or M theory, that's compactified theory, and it actually correctly predicts a certain amount of stuff experimentally and explains some other stuff. Would you call that theory unnatural if it basically got things right and you could calculate stuff? So I'll just leave that as a question for later during the talk. In a number of places on the east and west coast of the United States, you would definitely call it unnatural, even if it predicted everything right.
So could you define what you mean a bit? This is a theory you get to without tuning any.
Yeah, you derive it. Yeah, we can come back to that. I just want to bring the question up to partly forestall someone else bringing it up, because almost always when I talk, someone brings it up. Okay, now I'm going to turn to what's probably the most important single result, and it's relatively new, a few years old result. So consider moduli masses. The result is that, in a loose sense, which I'll make more precise, the minimum mass, the minimum eigenvalue of the full moduli mass matrix, including all the things you mix into it, is about the same size as the gravitino mass at the factor of 2 level. So many people have thought that for a long time, because the moduli are massless without supersymmetry breaking, so you expect something like that. The sort of most obvious physical argument is that, assuming moduli stabilization is all or mainly due to supersymmetry breaking, e.g. gaugino condensation, which certainly works in most cases, and if you consider then the full moduli mass matrix, including everything that can be considered a modulus, that includes scalar Gauss-Zeno contributions, which have typically the gravitino mass. There are complex 2x2 submatrix in there, or more. And that is a theorem that the smallest eigenvalue of a full positive definite matrix, which the mass matrix is in the region of interest, is less than the eigenvalue of any diagonal submatrix. So that's a sort of hand-waving, it's actually more or less correct argument, but you can still do better.
So axioms clearly violate this. Axioms clearly violate this, because it's easy just to have models where you have massless axioms.
The moduli mass matrix, I mean the positive moduli mass matrix, the positive definite, the real part of the moduli stuff, or the imaginary part, depending how you define it.
But so, if you have a complex, let's that says a minimal mass.
Axions are not. Let's not include axions for this discussion right now. We can come back to it later. Okay. The result is technically correct. Whoops. So here's the most formal proof. This proof was first written down by Douglas and Denev in 2004, and then a little later by Gomez Reno and Skruka, and then several papers by Skruka and collaborators are in a series. All of those were focused on either the stability of the vacuum or inflationary kinds of issues. We were coming from a completely different point of view and didn't know about this work, and we're looking at this connection from the point of view of the collider phenomenology and such issues, and the connection to the stabilizing the moduli, and we quickly learned about it after we started talking about it. If I sketch sort of the argument the way it's loosely there, but I generalize it a little bit because we wanted to consider studying some other things. So you want to calculate the scalar potential, you can make it a function of this, as you all know. Calculate the full mass matrix including the scalar curvature results, look near the minimum of the potential, then technically project along some unit vector. Technically the theorem about the lightest eigenvalue is here, and there's a proof here if you want it. We added projection not only among the scalar Gaussiano direction, but added a complex parameter just to see if we could learn something by studying some more things. You get a lot of nice things to study if you want, but they haven't turned out for us to be fruitful. Maybe they're more useful when you look at stability of the vacuum questions. So the bottom line from that set of arguments is effectively here that the minimum eigenvalue of the moduli mass matrix is the gravitino mass times this stuff. If the only scales in the theory are set by the Planck mass and the gravitino mass that you calculate from the Planck mass, then R is not large, typically 1 or less. For example, if you take simple isotropic G2 case with everything equal, it's 14 over the number of moduli, which might be, I don't know what precise number you want to use, but 50 or something. So you get some bound, which is useful if other scales are put into the problem by hand, one way or another. If you add other scales, there's nothing wrong with the bound. The calculation is correct, but it's in general not useful at all. That led Piyush Kumar very recently to derive a bound which is much stronger and more useful in a variety of theories. What he showed in the 2B case and the M-theory case is that if all of the contributions that are positive contributions to the potential, you could think of them as uplifting, so they're not the normal moduli that would give you an ADS minimum. If they depend on moduli only via contributions to volumes in such a way that the volumes occur as inverse powers, which is correct, which does hold for the entire G2 case of interest and a lot of the stabilization of 2B, in that case then the R dependence drops out and you get the bound without any R dependence. So in our review that I mentioned, that's given 1 page, and he claims he's going to post a paper any day, which is the full derivation of that.
Gordy, so there's something I completely don't understand about this. So this is 2 plus something which is positive. So that in that brackets, that's a number which is strictly positive because that's 2 plus the modulus of R. And so this is saying, but I can, so things like the large volume models, the minimum moduli mass is parametric.
So this is strictly positive only in this case where the full answer allows negative stuff up here if I went through it, and I'm just ignoring that for this talk because I'm not interested in looking at vacuum stability or in lots of other issues for here. So it's not strictly positive. I'm sorry, I should have said it more clearly. It's strictly positive for this case only. And the papers of Skruka and collaborators and Douglas have the full story in detail, although you can generalize it to these other curvatures as well.
So then this expression here is not a bound. I mean, this is not a theorem.
This is the bound in the case where R is not large, is of order 1 or smaller, and this result will actually also hold in Kumar's result, which is reported in 1 page of our review.
This is an upper bound, right? Not a lower bound.
It's an upper bound on the moduli minimum mass.
So it can be much smaller.
So yes, that's so the bound remains correct, but it becomes useless if there are other situations. So from our point of view, the bound is approximately saturated in the G2 case, and that's all I really care about today. But everybody who's working on things should pay attention to this bound and to the implications of that for what they do. And rather than take time for the talk, I recommend you look at the section 6B of the review. And we can talk about it later. I'll be here, and Piyush will be here for the meeting part as well, and he hopes to have posted the full derivation by then. So now you all know it's an old problem in the early universe. As the Hubble scale decreased toward the moduli masses, the moduli begin to oscillate in their potential. They quickly dominate the energy density of the universe. Once the early universe is matter dominated, very quickly after inflation starts, it's matter dominated, not radiation. So that's a non-thermal history, different from all of the standard radiation histories that people assume and work with. When the Hubble parameter gets down to approximately the moduli decay width, which scales, it couples to everything gravitationally, Planck suppressed, coefficient of order 1 calculable, at least approximately in any theory. Then the moduli decay, and the result that's been around a long time is that the mass of the moduli has to be, minimum mass of the moduli has to be greater than approximately 30 TeV, so that the decay occurs before nucleosynthesis. So this is an old result. It's been around 25 years. People have been trying to find a way around it for 25 years. Many of the, so far there is no way around it known. Many of the smartest people in the world have tried. When I talked at Princeton a couple years ago, Fan, Rees, and Wang told me after my talk they would quickly find a way around it and tell me soon. A year later, they wrote a paper saying they couldn't find a way around it. They found one technically not excludable detailed thing that can't occur in a string theory but could occur in a field theory, they said. But they certainly weren't going to claim it was physics.
What about the thermal inflation? Thermal inflation?
Well, that's an example. They tried for a year to find an example of thermal inflation that, and they said that they could exclude every example that was published that you could get out of a string theory.
And it's very model dependent because it's very local. It's a low energy, so you cannot have.
I'm only telling you what they said. Maybe they didn't get it right. They've read all the papers. They're smart. They talked to many people. They were highly motivated to prove me wrong. Or not literally me, but all the people who've said this, starting with Graham Ross, for example. And they gave up, basically. So it's up to, if people want to say that there are ways around it, they can say that. You, of course, never can prove something can't happen. So if someone can find a way around this, then they can find an exception to this whole thing, and that would be very interesting. So I encourage people who can do it to go ahead.
So, Gordy, one should also say that this depends on an assumption that after inflation, the moduli are away from their vacuum balance.
Well, you can look at all that stuff. You look at whether they can be trapped. So people have carefully looked at moduli trapping, looked at whether they were away. Yeah, it's true that if inflation ends with all moduli at their minimum and nothing moving away or anything, then you could possibly find an exception from that stuff. Then they're not oscillating. For example, they don't dominate. But that's pretty hard to arrange. And in practice, you don't get any kind of stable situation which gives that. So it does, you look at things like that, there's a long list of them, and the end conclusion is that from the physical point of view, this is probably the right answer, but I welcome more people looking at it and taking time and doing something with it. But I think it's worth exploring the implications of assuming this is indeed true. Then from the previous couple slides, that tells you that the gravitational mass has to be greater than about 30 TeV in any compactified string theory consistent with cosmology. Then you look at the supergravity field theory connection, which you expect in your field theory once you've gone to 4 dimensions after compactification, that tells you that the scalar masses, the squarks in particular, should be heavier than about 30 TeV. That means that it's a firm prediction about this structure that you will not observe squarks at LHC. Very clean, firm.
Again, so I mean, so for example, these kind of KKLT based models, I mean, they generally had a structure where the moduli masses were heavier by a log factor than the gravitino by a factor of 30, and the
Well,
soft terms were
they
lighter.
fit in the bound perfectly well. In KKLT, you have a situation that's described by it. You have heavy moduli, but there is a light modulus which satisfies the bound, makes the gravitino heavy. You can work out all those things. It's in the appendix to our paper, what the KKL2 stuff does. And other people have done it.
They all wrote papers saying that the modular mass is around 1,000 TeV, and the soft terms are 1 TeV, and the gravitino mass is 30 TeV.
I don't think there's a correct paper that says that. If you take KKLT as putting in a new scale by hand, by putting in their anti-D3 branes and fixing a new scale that way, then, as I said, you can change the results. But you don't get anything from the point of view of the theorem which violates it. In KKLT, well, Kumar will address KKLT in the sense also that the positive contribution, which does the uplifting for KKLT, is included in his argument, I think, of giving a, well, I'm not sure finally the outcome.
Well, that wouldn't
but
fit into the supergravity framework, so I don't see how.
Yeah, it doesn't fit in I don't know quite what to do with the non-supergravity parts. Kumar studied it, we can go back to it, but it doesn't change anything from the outcome of something like this that you get by normal compactifying.
But I mean, you can uplift differently in KKLT, and then you still get scenarios. I mean, using F terms and stuff, and then you get consistent scenarios where you have a 10 TeV gravitino mass, as Joe said also.
And no
TeV
cosmological
masses.
problems.
And no cosmological problems because you have 1,000 TeV moduli. There are consistent scenarios.
And now there's some, well, I don't remember finally what happened there. I'll have to come back to that. I'll try and remember by the end what happens there and come back to it. When you look at the non-thermal matter-dominated history then that you are led to by the compactification this way, two particular things stand out. One is in a paper by Acharya, Babkov, and Kumar. Because the universe is matter-dominated as it cools rather than radiation-dominated, then the upper limits on the axion decay constant that occurred phenomenologically get increased. And they go close to the compactification scale, not quite 10 to the 16 GeV, say, but over 10 to the 15. And so it basically solves the string axion problem in that context that's been long-standing, and you're allowed order 1 amount of dark matter. So there's a paper, I forgot to put the number here, but it was listed earlier. Then you can look at the moduli decay, which decay via the Planck suppressed operators to all the MSSM particles. And work out, you can't tell from exactly what I wrote here, but you can work out, for example, a modulus decaying to dark matter chi, or the critical density, compare them. You see that there's much more dark matter, and it must annihilate down after the moduli decay to not badly overclose the universe. And if you look at all the superpartners that could be the dark matter, only the Weno-like one, you could say pure Weno, but you know there has to, for example, be some non-zero mu value in any theory. So it's Weno-like. Only that has a large enough annihilation rate to do that. So in any picture like this that emerges from compactification, you expect that the LSP will be Wino-like. You can't calculate its mass from this kind of argument, and it's not a satisfactory top-down argument, but you can estimate in a framework that it's 1 to 200 GeV sort of mass, which we did. Now, before I turn to the Higgs and the dark matter data, let me actually summarize briefly the history of some of the work on M-theory, because it's poorly known to many people, although this audience probably knows somewhat more of it. But I'll quickly illustrate the history. So, and I'll do a couple slides of the string side to show that we're not totally ignoring such things. So historically, soon after M-theory existed, there was an important paper showing that you got to preserve n equal 1 supersymmetry if you compactified M-theory in a manifold G2 holonomy. Then a couple years were slow. Then Acharya talked about the singularities that come from the non-abelian, that arise on 3 cycles from orbital fold singularities, and you get non-abelian gauge fields. Then there was a series of papers that talked about the singularity structure and some details. The chiral fermions are supported at points with conical singularities. Witten made an argument that you probably could embed the supersymmetric standard model, but it's not a proof. It's because the global metric isn't known. People wrote down Kähler forms and gauge kinetic functions, and there's a kind of review by Acharya and Gukov in 2004 that's a pretty good summary of this period of work, and including detailed arguments about all the moduli in the M-theory case being geometric and on an equal footing, and a number of linear independence arguments. Then from the theoretical point of view, less was happening. Xingtung Yao had 2 students who he put working on it. He has one paper, and one of the students, Sergei Grigorian, who's now a postdoc at Simons, wrote effectively a review based on his thesis. The other students, Karagopoulos, approximately, at not perimeter, but next to perimeter. What's your university next to perimeter? Waterloo. Karagopoulos is there in the math department. And recently, Bobby and others ran a 1-week workshop at BAMP basically on what's the G2 manifold metric, with a number of mathematicians coming. So that's kind of the status on the mathematical side. Then, for some reason, this got printed in reverse order. So, but we started working in 2006, and wrote here, this second paper, for example, does write down the potential and show that you get the Sitter minimum and stabilizes the moduli. This calculates the spectrum in many details. This is about moduli physics. Then there's several other papers. This paper showed that the soft, you can calculate the whole supersymmetry soft breaking Lagrangian. This showed that all the terms in the soft Lagrangian have the same phase, so they can be rotated away, and there is no supersymmetry CP problem. This is the Axion paper I mentioned from Bobby and people with this archive number. The R paper after the earlier ones on the connection of the moduli and gravitino mass. One effort at embedding the mu parameter in the theory, starting from a discrete symmetry of Witten's and making a proposal for embedding it. Several phenomenological papers, and then the recent review. I did that quickly. I'm going quickly because I want to get to some of the connections to the data that are exciting recently, I think, more importantly. So you look at a number of detailed things about the singularities. You write down superpotentials. An interesting thing in G2 is that it's generic, that the 2 3-dimensional submanifolds that have gauge matter don't intersect in the 7-dimensional manifold, so it's gravity mediation generically in such theories. You go through writing the superpotential, you get gaugino condensation, typically from the gauge matter singularities. You can stabilize the moduli. You can explicitly show that you stabilize the moduli. You write Kähler potentials starting with the Beasley-Witten paper, and then some generalizations, basically 3 times the logarithm of the volume. Further study of approximations and such things to that. You look at the gauge kinetic functions, and there's some linear independence arguments, as I said in the Gukov-Acharya paper. You get a big potential, which you can semi-analytically minimize. Last point to make is important. You know, it's well known that if you only have moduli when you compactify, then you get ADS extrema, and no-go theorems and so forth, classically shown by Gibbons. And then I think the last paper of several was Maldacena and Nunez about 10 years ago. In the case of M theory, the chiral fermion condensates give positive F terms and lift you, if you think of lifting. You don't, it's not really right to think of lifting because the gauge singularities and the chiral matter singularities are just there. You don't put one in or the other, but if you think of it pedagogically, then you can think of that as uplifting. And you can actually trace that what happens. If you look at the ADS minima, what happens is that you're promoting a supersymmetry preserving saddle point. So the de Sitter minimum is near a point like that. And so when you calculate the gaugino masses, you look at the gauge kinetic function from the standard model stuff, and it involves the dominant supersymmetry F terms involve taking derivatives with respect to the chiral matter content, which aren't in the gauge kinetic function of the standard model. And so you don't get the dominant contribution from that when you calculate the gaugino masses. In addition, you come from near a supersymmetry preserving point where the gaugino masses vanish. So they're doubly suppressed. Gaugino masses are doubly suppressed compared to scalar masses in the theory, completely technically, naturally. You don't know things well enough to calculate precisely, of course, but you estimate a suppression factor, in our papers about 1/60th is
Sorry. Yeah, so nobody expects you to solve the cosmological constant problem.
Thank you.
However, I think the problem that people have had is whether you have, since you don't have fluxes, how you are going to even fine-tune it. I mean, if you read the boson and Polchinski, I mean, the whole point of having the fluxes is that you have this discretome, which is sufficiently dense that you will get solutions where the cosmological constant would be near zero. You don't have fluxes. So what replaces the role of fluxes?
Well, I think one can make at least 2 comments. First, it's not yet agreed 100% that the only solution to the cosmological constant problem is the fine-tuning. There are a number of other approaches, and if any of those work, then that could answer your question. Second, Bobkov has worked on that approach, on that question. His work has come to a halt because he didn't get a faculty job, and so he's left the field. But Bobkov wrote a short paper in 2009, and he has a much longer paper that he's working on completing, looking at the looking in the M theory case and the type 2 case, where he says he can do both kinds of calculations, at things like the 3 cycles and the gauge groups and all of the singularities there that give rise to possible vacuum structures. And he counts, and he says he gets a number of the same order as the Boussel-Polchinski flux number when he does that. So I don't think I can explain the details of that, but he does claim that, and he says it's very promising for being able to literally do the scanning in this kind of approach. So you can look at his stuff. I don't have another comment. If the only possibility is fluxes, and that's the only way to solve it, then our approach is probably not right.
So is there a published paper? I mean, no. Is there an archive number?
There's an archive number for his paper. Yeah, I have no idea if it's published. I don't watch that. Finally, in this direction, so there's a number of other results that you can get by looking at the compactification. So you compute the full soft breaking Lagrangian at the high scale. The terms are real. I mentioned the Axion version. I mentioned the approach to the mu problem. All flavor things are currently fine. We've checked in great detail about that. If a non-zero value for Bs to mu mu would show up in LHCb, then this would be wrong. There's no leeway there. We have made an argument that you get a nice approach to baryogenesis and simultaneously the ratio of baryons to dark matter from moduli decay after an Affleck-Dine baryogenesis, which I am not going to go into just because of time. I'll be glad to talk more about it if you want at the end, but the calculations there are not precise enough to be certain of the situation, but it quantitatively looks like a very good approach to these issues that fits in with all this. And as I said, we certainly don't have any embedding of the standard model in the manifold, and we haven't tried to make any approach to inflation yet in all of this.
Excuse me, could you remind us again, so what exactly goes into that scalar potential? It's two racetrack, or how did it work?
No, in M theory, the gauge kinetic function depends on all of the moduli. They're geometric, and there are some linear dependence theorems showing that they will all generally be there. The superpotential will be then the sum of non-perturbative terms with the gauge kinetic function in the numerator. If you have
how many? It doesn't matter.
If you have one term and you have a gauge kinetic function and you expand, then every modulus gets an interaction and every modulus is stabilized, period. Now it turns out if you only have one term that you don't get a good approximation in the supergravity limit. So you can take another one, but it's not racetrack in the sense of needing a difference of two terms or any such thing. One term is, from the pure point of view of stabilization, enough to stabilize it because, and that's in the Gukov-Acharya review, for example, because it depends on everything and they come in at an equal geometric footing. You can have any number you want. We did two, because with two you can do both numerical and semi-analytic work, and so we gave a lot of formulas with two, but we checked numerically with up to 5 or 10 that qualitatively nothing changes when you do that.
So if you have just one super term, you say everything comes in, but because these are all linear, I can just redefine the moduli. So effectively, only one modulus ever enters the superpotential.
Go read the Gukov-Acharya review, and they will show you that that's equivalent to doing that, to having them all since they're geometric.
But only one effectively enters the superpotential. You could always redefine them to do that. So then everything else has to come in via the Kähler potential. And the Kähler potential, you only know to some extent. You don't have, you're assuming this kind of parametric form for the volume as a function of the moduli. But that's more or less a guess. There's no. There aren't lots of explicit G2s where you actually have expressions.
Again, we don't know the metric. There's a paper starting with Beasley and Witten, and then 2 or 3 more papers that argue that is the Kähler potential for this case, the leading term in the Kähler potential, and that other corrections are there. So
I don't doubt that this volume is the Kähler potential, but it's the volume as a function of the moduli that I'm worried about. Because so saying Calabi-Yau's, you've got you say it's also the volume, and but then you often have these things like you have these G's forms, or you can have just toroidal forms where you have tau 1, tau 2, tau 3, and you seem to be making kind of a very particular assumption about how that will appear.
That part of the mathematics is not where I'm expert, but those guys argue that that's completely taken care of by the M theory case and the connection of that Kähler potential to the full geometric nature of the G2 moduli. So they address those questions and give you answers in those papers. And we just use what's in those papers when we did it in 2007.
Yeah, so I'm sure they're great people, I'm sure they're smart people, but it's just the thing of, if you don't have actually...
I don't have a full detailed technical answer for you
explicit G2s
because I haven't
to
worked on that stuff.
test
Well,
it against.
There are explicit G2 examples of Kähler potentials and gauge kinetic functions and so forth, but they're not ones that are known to be full metric satisfying examples, but there are examples in those papers. And we just use that in our later work. And I can't do it off the top of my head, and I didn't bring it. But, well, two answers. One is that I think what they've said in the literature is correct, and they're not misleading you. And second, Bobby and others will be here the last week of the meeting, and Bobby does have it all off the top of his head, so he can give you answers to any of those things. So I'm sorry I can't, but. Okay. Just a remark, don't sign on to gauge mediation at low scales. Now let me turn to the Higgs part of the predictions. So first, just for an overview and for the people who want to know the technical questions of how you calculate and do things. So you write the theory at the high scale, you fix the full soft breaking Lagrangian. There are no parameters in it. There are a couple assumptions, but no free parameters. Everything is calculated. You run down, you maintain the radiative electroweak symmetry breaking the whole time. Tangent beta is an issue in the sense that it's calculable in principle, but you can't do accurate calculations yet. Tangent beta should be of order 10 from the calculations. You want to maintain the supergravity relation, so mu is not in the superpotential. Tangent beta seems to always come out if we play with things a little bit to get a feeling in the range of 5 to 15. Technically, if anybody cares, we use several techniques, the so-called match and run technique that we do ourselves, and we use the programs like SoftSUSY and Svino. We compare, we match at that point, we use two-loop RGEs. The technical versions of what we do are comparable with the most complicated papers in the literature. I'll show you a little bit, it's kind of interesting. The biggest single source of imprecision for a given gravitino mass is actually the experimental top mass. If you vary the top mass by 1 GeV, experimentally you vary the Higgs mass by 0.8 GeV in the prediction. So you cannot avoid that kind of uncertainty in your prediction. Alpha strong gives about half that range for true standard deviation effect. The gluino mass has some effect, it's small, but we allow a variation like that numerically. And the trilinear couplings are determined, but we don't know how seriously to fully take that in a final general theory. So just to study it, we allow a little bit of variation. That basically the trilinears have to be about 1.2, 1.3 times the scalar mass in the soft Lagrangian, but we allow them to vary a little bit just to study it, and I'll show you the effect of that. We assume that there's supergravity in the field theory limit. If that's wrong, then we, I don't think, could that be mine?
No.
Okay. So the scalars all have a gravitino mass, squarks greater than 30 TeV, I said. We assume, now here's an important assumption, we assume that below the compactification scale, you have the MSSM, the minimal supersymmetric standard model. That means the structure of it. You calculate it, you assume you don't go beyond that at this point. That's a result we can come back to as soon as there's time, and we can allow extensions and see what they do, and we're actually have a student doing that. But for now, everything I show you will be assuming below the compactification scale. Your theory is the MSSM. Our approach is that you ask for solutions to string theory that have a Higgs mechanism, that is Higgs Devs non-zero, coming from radiative electroweak symmetry breaking, so at the high scale you don't have a Higgs mechanism. Then as you run down, radiative electric symmetry breaking induces one. We find many, many, many such solutions. We don't care about others. They're not our world. So our approach is just anything that can't be our world, we're not interested in working out any other predictions for it. And so we're looking for those, and we find them, and we use them and calculate in them. If you look at supersymmetry books, then because of the heavy scalar masses, you're in the situation of a decoupling limit. The other scalar matrices, the other scalar Higgs bosons are heavy. H is light, and we calculate the ratio of MH to MZ in this theory then. The calculations predict that the light Higgs should behave very much like a standard model one. We could not, if there are deviations greater than a few percent, for example, in the branching ratios or the production cross-section, then what we say is not correct. It's conceivable, but not likely, that it could be due to this if there was a deviation. We don't easily know ones that work. But our prediction in this framework, which is very, 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 very general, is very clear that the ratio of Higgs to MZ gives you 125 GeV. I'll show you carefully the results in a second, and it must be very standard model-like, and those are clean predictions. So I found to my surprise that people were accusing us of knowing the data before it was reported at CERN weeks before, even though I don't think anybody at CERN knew it weeks before. So here I show you the graph from August 2011, months before, that was shown at the International String Phenomenology meeting. The difference between what I'll show you in a minute and this is precision. This was a calculation of the central value. Then in the intervening time, we worked out the effect of the top mass and of many other things that could have affected the calculation and didn't finally, so that I'll just show you a few. But this proves you can go find it yourself. This proves that we didn't know ahead of time. Here's the final result. Here's tangent beta. Here's the Higgs mass. Here's 125 across there. I include 3 values of the gravitational mass because, of course, we don't know the gravitational mass from the theory. So we basically say it looks like 50 is a pretty good number for that. Let's take half and twice it and see what we get. So how to interpret this graph is look at just the central region between these 2 sets of lines. Then the scatter of all the blue points is the entire variation you could get by varying the top mass, the strong coupling constant, the soft breaking parameters, the Guino mass, everything is just given by the scatter of the blue points when the gravitational mass is 50. If you think you like a smaller gravitational mass, just shift the whole blue dot region down to here. If you think you'd like a larger one, shift it up to here. So for example, this is purely the region that you would get if you shifted it up to, this is the 50 TeV region, and those blue points just fill that region. So this is basically the final result from the whole framework. All of those blue points have mu small in the sense of a few TeV or so, and we have a separate argument for why we think that's right. But phenomenologically, all of these points simply have that. If you want mu to be large, then all the points that have mu order M3 halves are on here with red points, and they only come into this region below tan beta of about 5. And we can't, because of electric symmetry breaking, we cannot find any Higgs masses that work, any radiative electric symmetry breaking solutions with gravitational mass of 50 TeV and mu about the same as M3 halves and radiative electroweak symmetry breaking. So one point to take away is that basically you start from the string theory and you predict 125 GeV if the MSSM is the theory below the compactification scale. The other is we've actually studied a lot of detailed things which may help guide what's going on or interpret what's going on or do other things. So I'm giving you both in the sense that that's usually useful to look at.
Good. So, but couldn't one sort of take a an opposite view and say that just the MSSM by itself, and the previous LEP data would say that the Higgs would have to be between something like 115 and 130 Jeff.
Oh, well, people, if you take LEP data for the lower limit,
LEP data for the lower limit and say you've got the
then
MSSM.
most people would have said 140 for the upper limit because there are lots of examples of that, but well above 130. So of course you can say that. This has an accuracy of plus or minus 2 GeV, and it starts with no parameters except the assumption that it's the MSSM only, which all those other approaches do, and starts at the Planck scale, and you get 125 GeV with a precision of 2%.
Didn't that depend on tan beta and that your minimum
Well,
from the previous graph?
if I use the supergravity arguments for tan beta, then that's so this is the region we think it should be in. If you can even see here that you're losing electroweak symmetry breaking here. So yes, there's a variation, but look at 125 to 130, sort of plus or minus 2 GeV, because you don't quite know how to calculate tan beta accurately yet. If we do a straightforward supergravity calculation of tangent beta and the best approximation, we get 10, but it's not really reliable at that. It depends on too much of the radio, the connection and so forth. So this is what you get from a pretty strong start, and you can interpret it however you want.
So am I getting this right? I could make the following argument. I say I take the moduli problem seriously, and hence I have a very high Zusi breaking scale. And I accept the worsening of the fine-tuning problem a little bit.
There's no fine-tuning problem. I have a theory.
Okay, fine. But then, of course, I'm driven to this heavy stops and various.
I'll show you the spectrum
I
and things.
predict Higgs in the 126
Okay,
GeV
well,
range.
we can come back to that. First I'll show you the spectrum, and I'll show you those things, and then I can talk about that as much as you want. We also address the question of why you get 1 TeV scale, even though you have a heavy stop and so forth. So I can give you answers to those things, and I won't make it in
The
my...
Higgs mass comes from the heavy stop, right? That's
The stop is about 25 TeV.
stop.
Yes,
Yes, so this is the reason for this large Higgs mass.
yes.
Okay.
But it's coming out of the theory. We start with the Planck scale, and it's not a parameter. We don't fit it. We don't do anything to it. We don't change any parameters.
If I just for the sake of argument, would someone would tell me that M theory is not the right theory, I would still could make the argument.
You can interpret that if you want.
Okay.
If it predicts the Higgs mass correctly on the dark matter, and now we'll tell you some gluino stuff, if it gets all that right, you may want to hesitate before you say it's not the correct theory.
I'm just trying to make a simple argument that I can tell people who don't understand.
I can explain why it does it that way. I can explain to you why nature confuses a lot of young theorists.
Yeah, so how sensitive is this to the value of M3 half? In other words, if you say your lower bound for M3 half
right there.
is 30.
It's right there. It goes up.
Yeah, but
It goes up or down about 1.5 GeV if you double M3 halves. It's right there.
So it's very insensitive to and to tan beta also. Why the black band on the left?
Well, because we also calculated a curve which allowed large mu and which allowed small tan beta, but this is the one that we get out of the theory itself. So what I ended up putting up was one covering up the other part and doing this. This is the M theory clean result.
Could the gravitino mass be much bigger?
I know of no theoretical upper limit on a gravitino mass yet. I don't know of any way to calculate purely from the theory. Phenomenologically, there are several indications. This one, if your gravitino mass gets big, then the Higgs mass goes up.
So you're meant to be predicting the Higgs mass, and you say there are no parameters, but you put in the gravitino mass.
There are no soft breaking Lagrangian parameters except the scale. The gravitino mass, we're showing you the variation. So if you double it again, it goes up to here and so forth. Yes. So there are no theoretical arguments I know of that put an upper limit on the gravitino mass. There are phenomenological ones, so you start getting in more and more trouble with dark matter and relic density and the Higgs mass. And I'll go to if you allow me time, I'll go to the gluinos and LHC predictions. And again, they scale with it. So if it may be measured, but I don't yet know of any theoretical argument. So that's an interesting theory problem, is to write a theoretical argument which gives an upper limit on it.
Why are no blue dots above this line above you?
Sorry?
Why are there no blue dots above this middle band if there are no theoretical upper limits? I mean,
Above-
I think it's still
No,
spread.
the graph says if you want to have M3 SV100, just shift all the blue dots up into this band.
So in computing the blue dots, you assumed that it was small.
No, we do a separate calculation for the blue dots for all three of these. And then we draw an upper line, which is the boundary of the region for them. But we only show you, to minimize confusion, we only show you the 50 ones.
Okay.
But if you put M3 after 1,000, then you get up to 140 GeV Higgs?
I assume, yeah. I mean, we didn't calculate exactly, but I presume right. So if the experimental number is not 125, then...
But there's no theoretical argument for M3 half being 50, right? It's just phenomenological that you want it there. So then...
Well, it's just phenomenological, yes. There's a lower bound, which is also phenomenological from the cosmology. There's no strong argument for 50 that I know of theoretically, but there are a number of phenomenological ones, and I'm not sure how to interpret that. So let me turn, I will probably take 10 more minutes if you don't mind, but I've already had a lot of questions.
If that Higgs is detected in that range that your theory predicts, how can you tell that it's not the normal standard model Higgs?
Well, I'm sorry, I can't hear.
If the Higgs is detected at those energies, how can you tell that it is not just the normal conventional standard model Higgs, but it is part of this theory?
Oh, well, the best way is to find the gluinos at LHC, so let me turn to that part of the physics. Or the dark matter lattice superpartner, then you've settled that it's not normal. And that's not really hard to do. We can talk later about that. There are many other ways you can get indications about that. The cross sections will in general be different and such things. So it's not a problem, or it's fun. Okay, so here's this new stuff. Christoph Venegar, a postdoc in Munich himself, looked at the Fermi data, which is available. These two graphs are from Venegar's paper. I'm only showing them to give you a sense of what it's like. I'm not going to make any big argument about this is right or not. I'm going to just mention a couple things, and then I'm going to show you a number of tests, which will be done soon, regardless of the correctness of Venegar's paper or other things, to find out whether it's correct. So it's internally checkable. But I just thought you'd be interested in seeing it if you hadn't. So just look at the black points. There's an excess of about 50 in that and an excess of about 50. These two regions are just different space regions effectively, and these are the cleanest analyses. So I'm just showing you what's done. There's half a dozen papers leading up to one early this week by Doug Finkbeiner and Meng Su. Doug is, many of you may know, he's one of the most reliable people in the world, having worked with the Fermi data. He's done it repeatedly. He concludes that the analysis of Venegar is correct, and Finkbeiner says it's even stronger, that it's a real signal. So you can look at some of the evolution. I take Finkbeiner very seriously on this sort of stuff, which helps. But the important things are, well, first, implications. If it's true, then it is the first discovery of new physics beyond the standard model, period, and that's amazing. is also the discovery, if it's true, I think, of supersymmetry and of the dark matter. It's conceivable someone can make a different interpretation, because in physics there are always different interpretations of everything. So I'm not going to argue that's unique, but I think that's the correct thing. I'll show you that if we normalize to that mass, I'll show you how we get the number 145 in a second if you don't know, that it gives us gluinos in the range 800 GeV to about 1200, which are accessible at LHC. In our paper, we had fun and made an argument about axions being part of the dark matter too, but I'm not going to talk about that here. That depends on extra analysis. Tests. So the line comes from this box diagram. So the two lightest superpartners annihilate by a Chargino exchange, a W box diagram. And the dominant thing they would annihilate into is a photon and a Z, but there'll be another diagram with two photons, and the ratio will just be the coupling of the Z to the photon to the W, which is completely known. And kinematically, the energy of the photon in this case will be something, and then in the other case with the gamma, it'll be larger by 14 GeV coming out. So the LSP mass would be 144 GeV. I would say from the numbers people are reporting, there's plus or minus 1 or 2 GeV uncertainty in these numbers, but not more at this point. So you must see both lines, and the ratio must be correct. That's a great check. If that's there, then you have to see a second line. Fermi could confirm the first line and see the second line, although with the data in hand, they have a problem. The AMS detector on the space station has claimed in its literature that it can see these isolated gamma lines of this kind of energy and intensity, and they've taken data for a year, so they could at any moment report confirmation or not. They should have quite a bit more data than Fermi and quite a bit better precision. I'll talk a minute about the LHC because it's really interesting how it shows up at the LHC. The numbers are such that there's a possible problem with not seeing these lines from dwarf galaxies. At the level we're at right now, there's a sort of 2 sigma discrepancy between what we would expect and what Fermi's reported from dwarf galaxies. But they have a number of assumptions that go into that we haven't studied much. I'm not going to go through the details of Wenneger's analysis and that stuff. So that's basically the dark matter thing. It's reported, it's looking stronger and stronger. It's amazing if it's true, and there will be lots of activity and stuff showing up. So if we normalize to the LSP mass, then here's gluino mass, here's gravitino mass. The gluino mass is between about 800 and 1200 GeV then in this whole framework.
Does this involve gaugino mass unification? Do you have gaugino mass unification at the high scale?
No,
or
we don't have any parameters or any unification or anything. We just predict.
Well, what determines the gluino mass then, though? I mean, what determines the gluino mass? Because you said that it was that the gaugino masses were suppressed relative to the scales by some.
Okay, so I'm being unfair in that sense. Gaugino masses are suppressed, and I had a slide on the origins of the suppression relating to getting a de Sitter minimum and the 2 types of singularities and the fact you're coming from a supersymmetry point. So our estimate of the suppressed gaugino mass is an estimate based on the theory, but it is a factor of about 60. The tree level gaugino masses are degenerate at the high scale from the theory. That's predicted. Then they're suppressed. Then you include in the calculation the anomaly mediated ones, which are similar in size. You do the full calculation of everything, but the 160 of suppression is basically what we're tuning with the dark matter mass a little bit to make it work about right.
So the reason that you've only got really very narrow sort of distribution is because of the unification, essentially. I mean,
because of what?
Because of unification, if you say at the high scale or
the theory tells you that at the high scale, the tree level masses are degenerate, then we use the meson singularities, the conical singularities that generate a contribution to give you the suppression that you calculate. But finally, we get the dark matter mass correct with that suppression calculation, and then scale up the gaugino, the gluino mass, because the theory alone probably isn't accurate to a factor of 2. So now that adds accuracy for us there.
So the suppression factor was not determined from the UV theory, right? It was, you estimated it, and you fix it to the right size in order to give you the right dark matter.
1/60th wasn't a bad estimate, but the dark matter was within a factor of 2 of 145 at that point. Yeah, that's right. Thank you. Okay, so here's the full spectrum, 50 TeV gravitino mass. Higgs here, 3 of the 2 neutralinos, 1 and 2, and the chargino are light. These guys are heavy. The gluinos around a TeV. These are all heavy. You can see a stop at a little over 20 TeV is the lightest of the scalars from just the RGE running down. The gluino decay is typical. There's, for example, the top stop, and then at this vertex, the stop or bottom gives you, again, quark and chargino or neutralino. About half the time it's a chargino. And the 2 interesting things. One is that if you look at how much third family final states are favored, it's about a factor of 2.5 relative to first and second family because of the faster running of those scalars. Current published limits from Atlas and CMS do not in any way exclude this approach. There are no papers that exclude it at all at the present time. The lower limit that they exclude is about 750, that is below about 750 GeV gluinos. It would have been seen, but with this enhancement, which they do not include in their initial analyses and are only starting to publish analyses about, then this is all fine. The really interesting thing is that about half the time at this vertex, a little over half, you have charginos. And those charginos are degenerate with the neutralinos because they're in an SU2 triplet. And so the chargino lifetime, gamma c tau for our gluino masses is about 10 centimeters. So the transverse distance traveled here is in meters, 0.4, 0.5, 0.7, 1 meter. So those charginos go through several layers of the detector and can be seen. They're 145 GeV particle, now we know its mass. They go through 2 or 3 or 4 layers, acting like a big sluggish heavy guy. And then the charginos decay. You know from the SU2 triplet analysis they're degenerate, but the electroweak splitting is about 160 MeV. That's an old calculation people did. So the chargino decays to neutralino LSP plus pion. The pion can't be seen in the detector. So you have this chargino barreling along, and then it just disappears. So if you look for events, which has not been done yet in either detector, which a gluino kind of environment, so some jets and some missing energy, and then look for a disappearing chargino in that environment, about half of all the events would have one, except they don't make it out of the first part, but about 20 to 30% of all the gluinos will have a disappearing chargino at LHC that is very clear and dramatic. That, if it's seen, will, of course, find you gluinos and charginos, and it'll check that the dark matter mass is indeed the Weniger one, and so forth. So I will conclude with that. Data is the really cool thing. The Higgs data looks like it should look from compactified string theories with stabilized moduli, so I think that's exciting for string theory. and M theory compactified on a G2 manifold is getting a lot of things to behave about like they should on this side. We still have to deal with the embedding and the inflation, but most of the other phenomena are behaving about the way you would like them to behave in your string vacuum. Thank you.
So we've had lots of questions and we're a bit over time, so I suggest we just I'm sure we've got more questions, so if we just carry on the questions into lunch.
I didn't answer everything.
You will have answered everything by the end of lunch.
Up to you.